Okay, now we ended up on this particular slide here, and I told you about the rule. I kind of mentioned to you about the rule of chem clay. So maybe before we start that, we just recap the rule first so that we are all on the same page. Okay, the rules of chem clay basically says that the size of the U surface can change depending on the isotropic pre-consolidation pressure. And the base of the U surface lies within the elastic regime and is aligned along the URL, unloading, reloading line. Okay. Now, actually, after, I mentioned that afterwards. The elastic zone of the soil is the region below the U surface, and it includes the base, which is known, in this whole region is known as the elastic wall. And soil state within the elastic wall can change freely. Okay, this is the funny house I was telling you about. If you are, the wall is like your room. Within your room, you can kind of move around at will. All right, backwards, forwards, whatever you want, you know. But if you want to go from your room to the toilet, which is in another room, say from one elastic wall to another elastic wall, the rule is you got to climb up the roof, come out on the other side, and then let yourself down on above the toilet. So this is the way it goes. There's no corridor leading to the other room. Okay, so it's a, you think of it as a funny sort of a house. Okay, okay. So basically, this is where it is. Now we're going to go forward from there. In drain triaxial test, the stress path must follow a plane defined by this. dq over dp prime is equals to 3. Now what do we mean by that? Let me just try to orientate you back to this. This is the model. This is the v-axis. This is the q-axis. And the p-axis. And this is the q-axis. Agree? Okay. Now, when we say we have, we are not having, when we say that we have the drain stress path, when we talk about the drain stress path, we are talking about dq equals to 3 times dp. All right? Or dq over dp prime equals to 3. Am I correct? And in the stress space, that is the PQ plane. Let me just remove this soil, and we say we have a PQ plane here. This is a straight line that looks like that. Am I correct? Now, you are now going to generalize this out into 3-dimensional space. And there's one more axis. There's a P here, Q here, but there's one more axis, this axis, the V axis. So how do we generalize? Now, if you have an X, Y, Z space, you have a relationship that looks like that. Okay? I'll put it to you that this actually defines a plane in 3D space. Because when you project that plane onto this wall, you see a line back to the 3-to-1 line. You understand what I mean? So in actual fact, in reality, it is actually a plane. But the plane is inclined like that. So you think of it as a plane cutting through. I just remove this part so that you can see like that. The slope of this plane is 3-to-1. 3-to-1. All right? And so when you project this plane back onto this wall, you see actually the 3-to-1 line. You understand? Okay, so this is the concept. Now, so later on we're going to make use of this concept when we go into the animation. The second thing is in the undrained triaxial test, your state path must follow. So that what it means is that your path has to, in the drain test, has to move within this line, within this plane, must be moving on the plane. In the undrained triaxial test, we know that when you look at the floor of the house, remember when I told you, you look at the VP plane, and essentially when you look at the floor of the house, it's a horizontal straight line. Why? V is a constant. V is a constant, correct? Because when you cut it along here, V is a constant. In 3-dimensional space now, you imagine this is a wall that looks like that. When you project this wall, this vertical wall onto the base of the house, it is a horizontal straight line. You understand? So when you come into 3D space, you generalize out these rules in this fashion. Okay? So that when you project back onto the 2D space, you come back to where you start. Understand? Okay? So these are the rules that we govern our movement in 3D space, in the chem clay model. Now, I'm going to, in the next maybe 45 minutes to an hour, I don't know how long it takes, but because I'm sure you all will ask questions. Please, if you have questions, please ask. Okay? Why this thing like that? Why that thing like that? Okay? And the reason why I want you to ask is because although we haven't started on modified chem clay, and the exercise I gave you is on modified chem clay, the rule is exactly the same. The way the stress path move is very similar. All right? Just now somebody asked me why this stress path go backward, the other stress path go forward. We are going to deal with it now, so that after today, when you run the thing, you will be able to make sense of the result. You should be able to. All right? Although we don't do the modified chem clay until Monday, but to me the thing is largely the same. It's just that the shape of the U surface is different, slightly different. All right? So basically, this is actually a critical moment. This is actually a critical moment. So I will start up the first program, okay, to investigate the first example. Okay, let us do some simple orientation first. Let us try to get ourselves familiar with some familiar landmarks. Okay, this is the NCL, the normal compression line. See, this is the house. The tentage, the roof of the house. The pink line, the purple line, if you like, that goes through is the critical state line. That is the critical state line. All right, and this here, the blue line, you see the blue line, is the top of the elastic wall. It defines the top of the elastic wall. Now, just as somebody asked me why the wall is so curved, and the reason is because when you plot it on log scale, it looks like a straight line. But in fact, log of P prime, when P prime equals to 0, log of P prime is minus infinity. So in fact, the line is supposed to go this way. Is that all right? Okay. So if you look at the E log P, don't get deceived by the straight line. It's actually quite a curve. Okay. So essentially, this is the situation, and the axis, this is the P axis, this is the Q axis, this is the wall of the house, and this is the V axis. So this represents the floor of the house. Okay, the floor of the house. So essentially, what we first do, the first step of the test, is to bring the soil, isotropically compress the soil, consolidate the soil up to a certain level of mean effective stress. All right, isotropic compression. So basically, you can see right at the start, the soil is being isotropically compressed, and as it compresses, the P prime is climbing because it's going along the normal compression line. The P prime is increasing. And as the P prime is increasing, you will be able to see that the U locus, the U surface is actually growing. It's growing in size. Which is to say, if you consolidate a soil, you should get a larger U stress, a stronger soil. And to me, it does make, it is intuitive. It is intuitive. Okay? So basically, so it's consolidating. You can see the U surface changing itself. Okay? And what is the P dash? The P dash axis. Are you saying you want to know? Okay, the P dash axis is this axis. The Q axis is this axis. This is the wall of the house. This is the V axis. This is the floor of the house. V is 1 plus the void ratio. Okay, basically, I don't think that the number he assigned is absolutely correct. This number here, I would suggest you don't pay any attention to the thing, because even if you take it in terms of, I think he's using water content, if you ask me. Percentage, water content in percentage. So don't worry too much about the numbers on the axis. Okay, I suspect he's using water content. Okay, but essentially just look at the trend as it goes. Okay, so essentially, if you look at this, in fact, if you look at the p-axis, the numbers also doesn't make good sense in a sense. Okay, it's not kilopascal, of course, maybe megapascal or something like that. Okay, okay, or log. In fact, it is no, it's not log. It's definitely linear, but it may be megapascal or something. Okay, so essentially, if you look at it, okay, now what we have just seen, now at this particular point, he started shearing the soil, and you can see the change in the stress path. This part here is isotropic compression, and then this part is drain triaxial compression. And so the thing goes up now. Now you right up to here, you can see that we are actually tracing a path up to here, and we are already on the roof of the house, because this line is where the roof of the house meets the floor. Is that right? The roof of the house meet the floor. So we are already, the soil, so that's why people say a normally consolidated camp clay is a yielding material, a material on the point of yielding. So if you specify a normally consolidated camp clay, that material is on the point of yielding. In fact, for most soil model, even if you take a soft soil model or a hardening soil model, if you apply an OCR of 1, that soil is on the point of yielding. Okay? And it is intuitive because if you have very soft clay, normally consolidated, all you need to do is touch it, you leave an imprint there. Okay? So it all ties together in some sense. Now, so basically this thing now is going out in this fashion until at this point you start to shear. Now the important thing is when you shear it, you remember it has to go in a plane that is inclined at 3 to 1. And so you can see that inclined line coming up. And this inclined line is not vertical, it's following the roof of the house. Now what you need to do is this. Suppose we come up along here. Alright, we are down here now. And then we start shearing. What happens is that I take a cut through here. Imagine this plane now. This plane is here, but it also extends all the way up to here. Alright. So when you look at the intersection of this plane and the roof of the house, it traces out a line that looks like that. You follow? The intersection line traces out a line that looks like that. Okay? So basically I'll just shift it so you can see. So now the plane is like that. But you imagine this paper is extended all the way up to here. And you look at the intersection line between this plane and this surface. It actually moves up this way. Okay? And that is the reason why when you see a drain test compression path, when you look at it in plan view, you see the normal compression line, it moves inwards in this fashion. When you look at it, it moves inwards in this fashion. Remember when we did the critical state soil mechanics yesterday, the line is moving downwards and inwards towards the critical state line. And so basically same thing, this guy is homing towards the critical state line, but guided by this plane, this 3 to 1 plane. You understand? So basically this is what's happening. So this guy is actually homing towards the critical state line. And you can see the important thing is as it is going that way, okay, this is a drain test on a normally consolidated soil. The soil is actually hardening, you know, because the U locus is still increasing. The U locus is still increasing. So the soil is actually hardening as you go. The cyan line, this light blue line here, marks the top of the current U locus. The current U locus. Okay? So basically it's actually still increasing. And so you can see increasing and increasing. And so it basically is going up. And now this is the end point because you reach critical state. Right? You cannot go anymore. If you keep shearing, it will just stay there. It will just stay there. Why? Because at this particular point, this is the crown of this thing. If you take the strain increment vector, it's going straight up. What is the volumetric strain? 0. No more volumetric strain. Okay? So it reached critical state here. So now the next step is he simulate unloading. Okay? Now, this is the new elastic wall. This is the U locus. This is the new, you see the region inside there is the new elastic wall, the current elastic wall. Alright? So now if you start to unload, you will unload along, you see it's just like, okay, it's going, now it's shearing, and you can see it's running along the roof of the house. Okay, we start at this particular point, okay, just somewhere around the base of the house, and we climb up the roof of the house, and now we got to where we want. This is the room where we want to get to, and now we want to let ourselves down. Okay, the important point is this: when you do drain loading or whether you do drain unloading, you still have to follow this plane, because dq over dp prime equals to 3 is a condition you set as a drain condition. Alright, so supposing you are now here, let us now fast forward and say that we are here. We want to unload from here. You have to unload along this plane because it is elastic, but at the same time you have to follow the 3 to 1. So this unloading line is not a straight line. not a vertical straight line. Okay, so you will see that this thing is not a vertical straight line. This is the, now it is sloping. You can see the slope. Is that okay? So actually this is the way it goes. So basically you might say, okay, what does the stress strain curve looks like? You can see the stress strain curve basically down here. The Q is starting from 0 and it progressively rises all the way to the top. If you plot the stress strain curve, the stress strain curve will actually goes something like that. Okay, we will see it later on. It will go like that. This is the stress strain curve. This is for a normally consolidated chem clay model. Okay, so the stress strain curve will actually look like that. Now you realize this kind of stress strain curve is not something that you can generate with a Mohr-Coulomb, because the Mohr-Coulomb usually have a kink somewhere. When you generate a stress strain curve with a Mohr-Coulomb, you usually show a kink somewhere. Okay, but this guy actually is a smooth curve, and that's the reason why. Remember I told you just now, Andrew Schofield says that he was very amazed when he see that he put sand, a dilation rule, a stress dilatancy rule for sand into a soil, all right, and out comes a thing that looks like clay, and this is basically what he was talking about. So basically, essentially, what he's trying to tell you is what he's trying to tell me, and this is the message I'm relaying to you, is that whether you are dealing with sand or clay, chances are that friction and interlocking are the two main mechanisms driving the soil behavior. Okay, and friction is something we all accept. I mean, otherwise, why are we still talking about angle of friction? You know what I mean? Whether you have sand or clay, you can still talk about angle of friction. All right. In effective stress, we still talk about angle of friction. Right. So basically, this is the main thing. And of course, when you unload, you will go something like that. There will be a bit of elastic rebound, and then this line will come down. This is roughly how it looks like. Okay. Any question on the drain test? On the drain test on normally consolidated clay. Okay. The main thing that comes out is you must think of the plane cutting. That's why I say actually when you want to navigate this thing, your visualize. Okay, of course you can. There are many ways you can approach this thing. And in NUS, I do approach them in two directions. One is this direction. The other one is I want to show them a bit of mathematics because in the exam you have to have a bit of mathematics. You cannot do this kind of animation in exam. You see. So I will do a bit of mathematics for them, and I will also do a bit of mathematics for you, but I will cut it down a little bit so that you get the physical idea rather than the mathematical manipulation. The mathematical manipulation should follow logically. You know, they say mathematics is the handmaiden of science. So you must get the idea first. So to me, this is more important. This is more important. So therefore, it is very important you must understand how it actually maneuvers. That's why I told you earlier on that the 3D space and 3D visualization is far more important. Is that okay? P0 dash. Oh, the P0 dash. Where is the P0 dash, you mean? Here. Yeah, complete. Okay, the P0 dash is constantly changing. The P0 dash is constantly changing. Let me start the program again. See, as you go up here, the P0 dash is increasing all the way, right? The P0 dash is increasing all the way. As your U locus is increasing, your P0 dash is increasing. Yeah, it's the baseline. You can see it tracing out the red line, tracing out the thing. The P0 dash is constantly increasing. Even during the shearing, the P0 dash is increasing. You see the P0 dash is increasing at the top, the intersection of the red line. Now you see the P0 dash. The P0 dash is actually here. The P0 dash is now here. The intersection of the U locus with the baseline, the normal compression line. Right? So the P0 dash is actually increasing. When you compress the soil, a triaxial compression test, drain, the P0 dash is supposed to be, according to the model, the P0 dash is constantly increasing as you shear the soil. Because, why? Physically, as you do the drain test, the volume of the soil is decreasing. Volumetric strain is positive. The soil is undergoing compression. And as the soil compressed, the particle becomes more and more tightly packed together. And as the particle become more and more tightly packed together, you expect it to be stronger, has a bigger U locus. And so the bigger U locus must be defined by a larger P naught dash. That is the physics of the whole thing. You understand? Okay? So there is a good element of what we call self-consistency or inner consistency within that thing. Is that okay? Okay? So, and it is important you see that element of inner consistency. Okay? So now we see the P naught dash increasing. You just look for the base of this light blue line and the black line. That tells you where the P naught dash is. Okay? So if you look at it, it is increasing all the way until you reach critical state. Now, the P naught dash at this point is here. Now you unload, but the U locus will not change because when you unload, it's elastic. There's no plastic volumetric change when you unload. So when you unload, it is elastic. Okay? So the P naught dash will stay at the same place during unloading. Now, if you reload the soil, where will be, if you repeat the drain test from here, you shear the soil, drain. The stress path will go back up this way. And it will reach critical state here. So, in a sense, when you plot the stress strain curve, when you unload, you come down this way, right? When you reload, you come up this way, and then you will join up here and you go level, just like that, because it has reached critical state already. The red line gives the stress path, yes. The state path, actually. We call it the state. It's not just two quantity, but three quantity. P, Q, V. So it's a path of the state. The stress path just plot P versus Q. This is P, Q, and stress history effect. Is that okay? And it looks like overconsolidated soil, right? It is. That is what Chem Clay says to you. That if you do a drain test, all the way you fail the soil, you unload, you reload it, the soil will behave like an overconsolidated soil, but it will reach critical state instantly upon yielding. So you can't get any more out of it. That's it. You get what I mean? Because it has already reached critical state before you unload. Now you unload and you reload. You cannot expect to get some more things out of it. It's given everything it's got. You are talking about this baseline. Okay. Yeah, what you are saying, I'm just trying to get your question straight. Basically, are you asking that whether we can reach this baseline by consolidating all the way to here? Yes, correct. Okay, basically, maybe I'm not sure whether this is what you're after, but if I will just say that if you want, there is another way you can get to this point by loading to here and then unloading back to here. That you can, yeah, so there are two ways to get there. I mean, basically, all that it says is that on the roof of the house, you can move anywhere. Okay? Yes. Correct, absolutely. Because it will be overconsolidated. And it will be overconsolidated to a point whereby it is soft, just underneath the critical state point. So the moment you start to shear it, hit critical state straight away. Okay? Yeah, it is. Because you know why? This line, it will increase slightly. When you unload, you see the line is not actually straight. This line is inclining back. So basically, if you imagine, you're here, right? And you follow this thing, right? You follow. When you unload, you go along here, and then you reach here. The value of the mean effective stress here is smaller than the value of the mean effective stress here. And so there's a small amount of rebound. Yes. There's a small amount of rebound. I mean, the changing void ratio, I'm not sure where you are sort of coming from, but this is actually an unloading reloading line. All right, If you take a vertical projection between this, below this point, you are actually at this point. So basically, you have already effectively unloaded back from here to here, along the unloading reloading line. This is what the model says. But is that what you are asking? You want to come? Yeah. Yeah. Yeah, it will be. So if you look at the projection, okay, you are looking at the projection of this point coming down. Okay, the projection, it will start from here, right? If this is a vertical projection, and then it will move back as you unload. Not a straight line. It follows the unloading reloading line because your elastic wall, this thing, I think just now we had a discussion on this. This wall is not a straight line. It's actually curved. So you must understand it's curving this way. So therefore, the V is actually increasing. The V is actually increasing. You see? So that's why I say your visualization in 3D is very, very important to get this part right. This point, projecting downward. Directly below the critical state point, this point. This point. This one? This one? And which one? This one. Okay, this one is up on the rooftop. This is underneath on the floor. Okay, but if you take a vertical projection of this point downwards, you will hit this point. It will not hit. This is not a vertical straight line. This is not a vertical straight line. All right. So when you do a vertical projection, you will hit the floor here. So when this point moves from here to here, all right, this point, the projection will be seen moving from here to here. This one here? This point. They are both on the floor. They are lying on the floor. They are on the unloading reloading line on the floor. Which point? This point? Oh, okay. I know where you're coming from. Okay. Let me kind of explain to you. You were originally here. All right? And then the red line, the second segment of the red line going up is this line, coming down this way. And then you unload from here. You go inwards that way. Okay? So imagine now I shift this thing over to here, just to show you how it's unloading. So now, supposing you come down to here, and then you climb up to here. All right? And then you unload from here. You don't unload vertically down here like that, because you are doing drain test, not undrain test. You unload this way. Yeah, there's a bit of rebound, yes. A bit of swelling, yes. There has to be a bit of swelling. You see, there has to be a bit of swelling because, you see, when you unload, okay, delta P dash equals to 1/3 of delta sigma 1 dash plus 2 delta sigma 3 dash, correct? All right. In a triaxial test, in a drain test, this is 0. There's no change in the delta in sigma 3, so this part disappears. But during unloading, this is negative. So in fact, your P dash is decreasing. You see, your P dash is decreasing. That's the main thing. The mean effective stress is actually decreasing. Okay, that's why the chem clay is different from the Mohr-Coulomb. The Mohr-Coulomb says that your shear stress has to exceed a certain level before you hit the U surface. The chem clay is saying that, you see, if you look at the chem clay model, the chem clay model essentially says that, okay, this is the chem clay model. Basically, the chem clay model is different from Mohr-Coulomb in the shape of the model as well, in the shape of the U locus. Okay, the chem clay U locus, you look at it this way. The chem clay U locus has some similarity to the Mohr-Coulomb. The similarity occurs this portion over here. This portion is a bit curving, but if you think of it as looking like going up that way, it looks a bit like a Mohr-Coulomb U surface. Mohr-Coulomb U surface, because it's also going up, Mohr-Coulomb. Except that the Mohr-Coulomb is a straight line. You think of it as a straight line envelope, but this is a curve. All right? Okay? So we won't argue whether a curve is correct or a straight line is correct, whatever it is. But where the chem clay has a bit of extra is this particular thing. And this particular cap is what I call a compression cap. The purpose of the compression cap is to say that the soil will not yield just under shear stress. It can also yield under isotropic loading. And so when your isotropic loading reaches this level, here it will start to yield. Because otherwise, you cannot explain this phenomenon. This phenomenon of this thing. You see, what we are saying is that this is isotropic. This is on the floor of the house, no shear stress, no deviator stress. But when the soil comes up to here, it yielded. Now, you can't explain that with the Mohr-Coulomb, because the Mohr-Coulomb will tell you it will never yield, because it's isotropic. But in fact, the soil did yield. So that is the advantage of the chem clay, that it is able to model this particular thing. So you don't need a shear stress to yield. Okay? A very high isotropic stress, a high isotropic means effective stress will actually be sufficient to cause the soil to yield. But you have to be careful with chem clay. Chem clay yielding is not failure. Yielding is not failure, because when you yield, the definition of yielding is the point at which you start to get irreversible strain, plastic strain. But it doesn't mean failure, because failure means just everything go flat. No more extra. No more extra. In this case, the guy has irreversible strain, but there is still extra. So yielding is yielding, failure is failure for chem clay. Very, very important to see that difference. Okay? So chem clay is not saying that when you compress a soil isotropically, it will fail. No. It never say that. All that it says is that up to a point, you will suffer irreversible volumetric change. And this is irreversible volumetric change. Because when you go up here, then you come down here, can you go back up here, down here? You can't. That's irreversible. That's yielding. Yeah, of course. But the fact that chem clay allows it to yield, in fact, in the next one, you will see why it is able to generate that kind of method A kind of stress path going backwards. That is the major advantage. That is one major advantage of a cap model. And the soft soil model has a similar cap. I think the hardening soil also has a similar cap. The cap Drucker-Prager also has a similar cap. But they all follow that. They all started with the chem clay. Because it is that particular thing, the recognition that you have that particular cap. That says that there has to be a limit on the mean effective stress. Beyond that, you will get yielding. Yes, Mohr-Coulomb. Yes, absolutely. But the pre-consolidation effect of pre-consolidation pressure is a statement related to this, because the pre-consolidation pressure is the isotropic pressure at which you yield. Correct or not? No, Mohr-Coulomb. But I'm not saying Mohr-Coulomb is no good. I think I also use Mohr-Coulomb. In a lot of my jobs, I use Mohr-Coulomb. But I will use Mohr-Coulomb if I know this soil has an isotropic yield point that's so far out, I don't have to worry about it. That I'm never going to heat it, I'm never going to heat it, so why should I bother about it? If you have a very stiff soil or a very dense sand, I'm not going to cause it to go that. It is not going to show this kind of behavior over here. Right? If this is very far out, for some kind of sands, they say that the isotropic pre-consolidation pressure is of the order of a few megapascal. So if you think that your job, the kind of loading you get is not going to reach a few megapascal, you don't have to worry about it. But for soft clay, you do have to worry about it. Okay? And the problem with the method A always occurs with the soft clay. You get what I mean? Okay. Ken? Clear? So in that case, if that tunnel is very deep, then that clay can have, soft clay can have. Oh yeah, it can be normally consolidated if it is deep enough. I mean, the question is how deep is your tunnel, you see. All depends on how deep is your tunnel and how soft is the clay. You see. I mean, if you look at the Nickel Highway project, the clay was about, the strength ranges anything between 10 kilopascal to 35 kilopascal at 35 meter deep. Now that is definitely a soft clay. All right. Of course, you have some very, very heavily over-consolidated soil in Singapore, that has got strength like 500 kilopascal. Then you kind of realize, oh, it's not going to happen. You know what I mean? So it depends on how deep is a tunnel. You know, so when you say deep, it's a question of, I say yes, in principle possible, but all depends on how deep you are talking about. Oh, half a kilometer down possible, but half a kilometer down, I thought you hit rock already.
Yeah, that's what I'm talking about. If rock have a fracture or a fault zone,
Mm.
then in that fault zone you might find that soft clay, which
Yes.
comes in with the water seepage.
Yes. But if you're asking me whether how would I model that particular fault zone?
Yeah.
That depends on how thick or how thin that fault zone is. How thick is it?
Generally it is
Hairline?
2 times the diameter of the.
Oh, the fault zone is that thick, 2 times the diameter. Yes, I think it is possible you could have a normally consolidated situation. But I thought if your fault zone is a hairline, if it's not, if it's just a hairline, all I need to do is, because there will be no compression, right? It's just a hairline anyway. So I would model it as a shear zone rather than anything. But if you tell me it's 2 times the diameter of the tunnel, yeah, it is possible. Definitely possible. Okay. But a lot depends on the circumstances. So it is very situational. You have to look at the situation. This is where you got to use your engineer's judgment to decide whether you think it's going to get whether the compression effect is going to be significant. But my sense is that if it's twice the diameter of the tunnel, I mean, in the first place, it's bigger than the diameter, the tunnel itself. So it definitely has some pretty significant effect, I think. I thought it was something like a shear plane, you know, and then you don't have to. Okay. Okay. Let's look at the normally consolidated undrained. Now, just now we saw a normally consolidated cam clay under drain loading. Okay, this is a normally consolidated clay under undrained test. Undrained test, and this is important because remember in an undrained test, we follow this plane. We follow this plane, right? So basically, you watch what happened. So this line is coming down. This thing is coming down. As before, it's isotropic compression first. Isotropic consolidation. So isotropic is a CU test. First, isotropic consolidation. Okay, this is the end point of isotropic consolidation. The shearing starts. Okay. Imagine now we have consolidated the soil to here. All right. And now we've got to shear it. We've got to follow this plane. The intersection of this plane with this that passes through this point. Okay, it traces out a line that looks like that. You see that? It traces out a line that looks like that. All right, and that line, you can see this line. If you project this line, this curve line to PQ space, it is a curve going backwards. But that's exactly what you want to generate the positive excess pore pressure, and that's what we see for real soil. The stress path is actually going backwards. Okay, so now we see this thing going down this way. You can see the stress path. The state path is now climbing up because it is trying to reach the critical state line. Okay, so basically you can see the red line, the red curve over there, all right, this red curve over there, all right, this red curve over there, all right, is going up all the way to the top. Okay, all the way to the top. And this red curve is actually following an imaginary plane that's cutting through the original point, the original pre-consolidation point, which is this point, You follow? So far, okay? Anyone, any questions so far? Because there's a subtle point coming out next. And the subtle point that is coming out next is this. Remember just now, a lot of you were asking questions about the leaves going curve. So in fact, the leaves are curved. But this plane is straight. All right? So the plane does not lie on the leaf. A single leaf doesn't coincide with this plane. This plane actually cut through numerous leaves. You get what I mean? So if you look at it in plan view, what you actually see, if you magnify out the thing, don't need to redraw. This is one, this is another one, this is another one. Now, if I start from this point, and I start to draw a horizontal straight line, which is a projection of my plane, that's a projection, and I cut across this way, I will cut across a line here, a line here. These are all elastic walls. So I'm actually cutting across different elastic walls. But as I cut across from here to here, you actually see that actually the P0 prime, the P0 prime is actually increasing slightly. Not by as much as a drain condition, but it is increasing slightly. And that is the reason why when you look at this thing over here, you see the current U locus as it reaches the critical state line, the current U locus is slightly bigger than the original U locus because the P0 prime has moved forward a little bit. Okay, so this, when you project now, think about it, you project this curved line onto the wall of the house to get the stress path. Project it there to get the stress path, you will get a stress path that looks like this. You start from here, all right, and then you go this way. This is a stress path, but this is the kind of stress path you want to see for soft clay. This is the kind of stress path that the Mohr-Coulomb cannot do. Mohr-Coulomb will do this stress path for you. And that was the method A problem. You see? So in a sense, you can say that all the soil models, not just the camp clay, all the soil models that has a cap will potentially be able to, in a sense, to a greater or lesser extent, solve the method A problem. You get what I mean? Okay? So this is the essence of the situation, that you need a cap, a compression cap, this particular thing over here. You need this thing. You need this portion of the U locus, this portion here, to actually solve that particular thing. All right? That's why soft soil model always have that cap. Whether it's called soft clay model, the Plexis soft soil model, or whatever, they always have this cap. Clear? All right. Now, I'm not teaching you Mohr-Coulomb because I think that you are going to use Mohr-Coulomb or that it is the best. But it is the simplest. And if you know Mohr-Coulomb, when you read up the soft soil model, you will know how to make sense of it, at least in the theory manual. Is that okay? That is the thing. Because I can't possibly teach you everything in the world. But at least I give you the framework so that when you read it, you know, yeah, this is what it is all about. Clear? Okay? That is heavily over-consolidated. We will work on that later on in a short while. Okay? So this is normally consolidated. What you're saying is what happened on the other side, this side over here, right? This, okay, we're going to come down to it. Okay? So basically, so far, this one okay? Anything else you want me to clarify? Okay. Okay, now lightly over-consolidated drain test. Lightly over-consolidated drain test is similar, but how to get the lightly over-consolidated state? You allow a bit of swelling going back. So now this is fully consolidated. Now what he does is to allow the stress path to come back a little bit by allowing it to swell isotropically. So it's swelling isotropically. Clear? Okay? So swelling isotropically, then now he's starting to load here. Okay, triaxial compression. Okay, now this is not a vertical straight line. This is following the 3-to-1 plane. Now you can see that at the start of the thing, there is a straight portion. There's a straight line portion, this portion over here. This is because the soil is over-consolidated. And over-consolidated soil will, according to the camp clay, always have an elastic zone. And so this is the elastic zone up to here. Okay. And then once you reach the roof of the house, then you start to go plastic. Then you start to swing across, okay? And then you can see the thing is going up this way, and it's heading towards the critical state line again. It's homing towards the critical state line, okay? Now you can see that this one, I think the way he write the program, somehow he didn't manage to get to the critical state line. It just stopped short of the critical state line, but the idea is the same. Essentially, once you get to the roof of the house, the material start to strain harden. So if you plot the stress strain curve for this material, the stress strain curve for this material will show you a straight portion which is elastic, and then it just goes this way. Okay? No need, because later on I'll give you the program, then you can just run. Okay? You take a may not have the kind of effect. Yeah. After swelling, yeah? This is swelling, this is a swelling stretch. You start to do a triaxial compression. But because the soil is over-consolidated, the U locus is here. After you have done swelling, you're on the floor of the house, right? So the U locus is up here, so you have to, this portion here is elastic. Sorry? This is gone plastic, yeah, this is plastic. Because once you reach the roof of the house, it goes plastic. Is that okay? I know for those of you who have done this before, it probably is quite natural. For some of you who have not done this before, you probably will need some time to kind of orientate yourself. But you realize the importance of 3D thinking. You know, I emphasize the importance of 3D navigation on this space because I know that a lot of people misunderstood Chem Clay, very senior academics from China. I'll tell you a story afterwards. Quite interesting. But it shows you how much people can misunderstand Chem Clay. Okay? And Chem Clay was nothing new. I mean, it started in 1950s. You know? Now it's 65-year-old. And yet, there are people who do not fully understand it. People who are supposedly very senior academics published paper on Chem Clay and yet never understood Chem Clay. I'm surprised. I'm really shocked. Okay, but this is where I think, you know, you need a proper understanding. So basically, then you start to unload. Okay, the unloading is the same as before. That is slightly over consolidated. Now, the next one is slightly over consolidated, but undrained testing. Okay, so now it's normal compression, isotropic. Then he has to go back, allow it to swell a little bit. This is a swelling phase. He's coming back. Swelling phase. Okay, this is the end of the swelling phase. The start of the shearing phase starts here. Now, after you have swell, you are basically, imagine now you consolidate all the way up to here, and then you swell it somewhere down here, right? You get somewhere down here. And then you come along and say, okay, now I want to force a plane cutting through this point, vertical plane, and that thing has to sort of meet this, come up, basically has to follow this plane all the way up. Now, you realize one thing. If you have this one, suppose you're at this point, below the plane, along, you're now sort of coming up to here and then come up to here. All right, okay, and now you put a plane cutting through. This is the floor of the house, cutting through here, vertically looking at it. So basically, this is the unloading, reloading line that you are currently lying on. You are lying on here. So this is the location. All right, but this guy is on the floor of the house, and this thing is up here. And the condition is that it must stay within this wall until it reaches the U surface. Remember that? It must stay within this wall, this U locus, until it reaches the U surface. It must also stay within this plane. Right? How can it go? The only way it can go is to go vertically upwards. Correct? You got two planes intersecting. One plane is a curve like this. The other plane is a plane that looks like that. When you intersect them, you get a vertical straight line coming out. That's the reason why you get vertical stress path. You see, so the vertical stress path is also consistent with this, that you should get a vertical stress path. Okay, so now you can see this part of the stress path is vertical until it reaches the roof. Until it reaches the roof. Now somebody asked me just now that when you run the program, there is a straight portion, then it turn back. Remember that? This is the straight portion. So you can see this is the straight portion. It's climbing up. When it reaches the roof, then you start to see it turn around. Is that a kind of trend you have on your stress path. As you turn around and hope, reaches towards go towards the critical state line, the line starts to turn back. So if you plot your stress path will look something like that. Your stress path will look something like that. Up and then come up this way. Is that how your stress path look like? So that's basically how you explain it. The first elastic portion follows the elasticity rule, which is a vertical straight line. The second portion, verticoplastic, is the part that you start to generate excess pore water pressure. So the important thing is this. The excess pore water pressure generation is both a function of the type of soil that you have, plus also the overconsolidation ratio. Okay? The more overconsolidated the soil is, the less excess pore water positive excess pore water pressure you generate. And if you have a very, very heavily overconsolidated soil, you tend to generate negative excess pore water pressure. You understand? So a normally consolidated soil should, in principle, generate the highest excess pore water pressure. Is that okay? Yeah. Okay. Basically, the elastic vertical part is something you need to imagine in 3D. Now you come up to here. You come up to here, and then you allow it to swell back to here. This is here. But now you're not on the roof of the house. You're below the roof of the house. You're somewhere down here. The roof of the house is down here. So when you force it to move along this plane over here, the only way you can move is to go up, straight up, until it reaches the roof of the house. Then you can swing over. Because while it is inside here, it has to follow this wall. It has to follow this wall, and it has to follow this plane. The intersection of your wall and the plane gives a vertical straight line. You got it? Yeah, the stress path is going this way. It's following this plane. No. The stress path is the same in elastic as in plastic. Because when you project it onto here, everything looks like a 3-to-1. It's only when you look at it in plan view, then you see this guy coming down. That's why the drain stress path is very boring. The undrained stress path is more interesting. For the drain test, we usually, the more interesting part is in the compression curve, when you look at the plan view. So there are two views. In the undrained test, this view is very boring because you just go this way. All you see is it going this way. All right? The stress path is more interesting in the undrained view because you can see it going this way, moving backwards. In a drain test, the stress path is very boring because all you see is a straight line going up, down, up, down. That was exactly what I showed you in the floor test. The flow come up and then down. That was exactly it. But in this plane, it is a lot more interesting. Go up this way, go down that way. You can see a lot more things. Okay? So in the drain stress path, in the drain test, you may want to pay a bit more attention to the compression space, the floor of the house. In the undrained test, you want to pay a bit more attention to the wall of the house. Okay? I can show you some example of the things that we plot. I usually make my student plot all three graphs. Stress path in the center, stress strain curve on this end, compression curve on below. The L-shaped configuration, because they share same axis. After I show you what I mean. Is that okay with this one? Okay? Now I'll show you just some of the things that I get my student to use. Because when you study, you want to have you see, the important thing is when you plot test result, you want to get a full picture. You don't want to get part of a picture, so you want to plot the full picture. Okay, I usually like to get the guys to plot this thing. Okay, you can see there are three plots, essentially three plots. The three plots here are as follows. On the left-hand side, I know this looks totally incredibly confusing, but on the left-hand side is the stress path plot. This is the wall of the house. All right, this is P dash, this is Q. All right. On the bottom here, at the bottom here, you can see at the bottom here, this is the floor of the house. This is how the thing compresses. So when you do drain test, when you do a drain test, you can see the drain test is very boring, the stress path. But on the floor of the house, you can see a lot of things going down and then coming back. You can see more interesting thing. Then on the right-hand side, okay, and the reason why I've asked them to plot this way is because you see the x-axis over here, and the x-axis over here is exactly one and the same. The two x-axes are the same. This plot, the stress path plot, and the compression plot share the same axis, and I make them draw on the same scale, so you can see exactly how it's going. All right. Then the third plot is actually the stress strain curve, deviator stress versus, I'll just use this, deviator stress versus the shear strain, the generalized shear strain. This is deviator stress versus generalized shear strain. Once again, I make sure they plot this axis on the same scale as this axis, because the same axis, deviator stress, deviator stress. So you can see when you map this guy over to here, how the stress path, how the stress strain curve is changing, how the compression curve is changing. See, it gives you a full picture, all right, of the complete response of the specimen in terms of the stress path, in terms of the compression, in terms of the stress strain curve. Okay, so this is usually how I like to get it to draw. Okay. Okay, so basically you can see that, for example, if you do an undrained test, then this portion here, this part here will show up as just a horizontal straight line, and you can't see very much. Whereas down here, you'll be able to see a lot of things going backwards, or going forward, or going whatever. Okay, so basically this is how you can, I mean, this is one way you can actually, this is how you can look at the thing. Okay, the last two, heavily overconsolidated. Somebody asked me, hey, what if you're on the other side? Yeah, you see, we have looked at the soil all here. What about here? What about this side of the thing? This side of the thing? This side of the thing? What will happen? That is heavily overconsolidated behavior. So let's start with the heavily overconsolidated. Okay, again, you can see isotropic compression, isotropic consolidation of the soil, U locus expanding, going out, and then now swelling. It's now swelling back all the way to here. You see that? All the way to the other side of the critical state line now. It's on the dry side of the critical state line. So now the guy is somewhere down here. You come down here and then swell it all the way back down here. It's down here. And now we're going to load it, and you still have to follow 3:1. No choice. All right, that is the drain condition. You follow this. So basically the guy will come up here, and then he'll come down here. All right. So you see how it goes. It's coming, it's shearing 3:1, but it is staying within the elastic wall now. Up to this point, it's still elastic, it's in the elastic wall. And now you reach the roof of the house. It has reached the roof of the house. It is coming down. Because you cannot go the other end. You realize that if you go the other end, he's diverging from the critical state line. He's diverging from the critical state line. The only way you can converge towards the critical state line is to come down this way. Now, what does that mean? You can see when it's coming down this way, the P dash is decreased, P naught dash is actually decreased. The U locus is decreased, strain softening. It's strain softening. But the void ratio, the specific volume is increasing, which means the sample is dilating. So it's dilating and it's strain softening. Okay? So this is the peak strength. When it reaches here, it's the peak strength. And it's now coming down. So when you look at it in 3D, it's coming down this way. You just imagine now you got this thing, this other end here, and now you're on this point. And you got this guy over here. This guy is sliding down here towards here. So as you slide down here, the Q is decreasing. Q is decreasing. The deviator stress is decreasing. So basically, it's now decreasing. You can see it's decreasing, sliding down the roof of the house towards critical state. Okay, and then unloading from there. So basically, this is a strain softening phenomenon. So chemically does allow a certain measure of strain softening. And so what it does is that during strain softening, the U locus is actually decreasing in size. Okay, the specific volume or the void ratio is actually increasing. And it is consistent with the fact that it is on this side of the critical state line. It is on this side, Because when you take the strain increment vector, it's pointing backwards, indicating that the volumetric strain increment is negative and it is dilating. Okay? So you must see that internally you have see all the consistency there. They are all consistent in that sense. Oh? So they tie in very nicely into each other. Everything is all internally consistent. Now, so if you plot the stress strain curve, what would the stress strain curve look like? The stress strain curve will show you that you have an elastic region going right up to the top, but this is the peak strength, and then coming back down towards critical state. So, in essence, chem clay will predict something that looks like that. Okay, so basically, what is this peak strength? The peak strength is the first point when you reach the U surface on a heavily overconsolidated soil. And the critical state strength is somewhere down here. You understand? Okay, so the peak strength is the point where the peak point is the point where you first hit the U locus in the chem clay model. Now, of course, real soil will not show you a sharp peak that looks like that. It will probably go like that. Agree? It will probably more look like that. Okay? But what I would say is this: when you compare with Mohr-Coulomb, I don't think Mohr-Coulomb can ever produce something like that. This kind of effect. Right? Mohr-Coulomb is either you go straight and then this way, go straight this way, or you go straight and then with a bit this way. That's all. You get what I mean? So at least qualitatively, I would say that qualitatively, on the dry side of critical, chem clay is able to explain why you get strain softening. Explain why. It doesn't model it very well. A lot of people know that. In fact, yeah, I wouldn't use, if you want to investigate, if you want to model a soil on the dry side of critical, I wouldn't use chem clay. You know why? Because the weakness of chem clay is in this region, the elastic region. It assumes that the soil is linear elastic, which is wrong. Actually, for this kind of heavily overconsolidated soil, very often one of the main concerns is deformation on this part of the curve, which is the non-linear pre-U portion. Okay, so a lot of people basically would use a non-linear model like a hyperbolic model or a Mohr-Coulomb model, but with a non-linear stress strain curve. That's what kind of thing that Richard Jardine used. You know? Mohr-Coulomb, but below the U surface, they just put in a non-linear stress strain curve. Okay, which is supposed to give you a better protection of the deformation below the U surface. Okay, because for that kind of soil, most of the deformation takes place before the U surface. Actually, once you get past to the peak point, in fact, a lot of codes do not allow you to design on this stretch because it is a strain softening stretch. A strain softening stretch is a very unstable stretch, you know, because if by chance you incur a slightly larger displacement, your strength of the soil will drop and it cannot take the stress, and then it will move forward some more, and one thing lead to another. You'll be soon sliding down this whole thing. So it's a very unstable region. So a lot of codes will not allow you to operate on that region. Okay, so this is the how the chem clay would model a drain test. Okay, on a dry side of the critical state line. I think someone was asking how come there's no peak strength. You see that? So this is actually, you see what Henkel has done is that he has done a very careful series of tests. He knew that very often in undrained tests in heavily overconsolidated soil, you will not get this kind of thing. You will get a peak strength and then it come down together with the shear plane. Now, in order to produce this kind of behavior, you got to suppress the shear plane. There are some ways people use to suppress a shear plane. If you use a very short sample with a frictionless end cap, you can, in theory, suppress the shear plane so that the shear plane cannot develop. Now, once the shear plane develops, then you have a very complicated situation, because what happens is this. Once the shear plane develops, the soil in the shear plane will start to dilate, but it will draw water not from outside the soil, not from outside the sample. It draws water from inside the sample around the shear plane. on both sides of the shear plane. So the water content in the shear plane will be higher, the water content in the outside the shear plane will be lower. There is a complete non-uniformity there, and your small sample doesn't behave like a material anymore. It behaves like a boundary value problem, like one of the rupture plane around the tunnel kind of thing. The stress state outside and the stress state inside are two completely different things. Okay, so Henkel is a very good experimentalist. Okay, he knew that this has to be suppressed. So I'm sure he actually took steps to suppress that particular thing. Okay, and that's why he got something that is not really falling. You don't really see the thing falling. Okay? Okay? And that is in a sense, at least in trend, qualitatively, qualitatively it is comparable to the chem clay model. Okay? Okay, I think the 6th demo has finished, and I think they said they wanted the exe files. So you want to use the Dropbox server, or you can use the other way, just Dropbox and just email the link to them and just give it to them. Very big, 40 megabyte, 50 megabyte. 40 big. Each file is 40 megabyte. Some are 70 megabyte. Yeah, you can upload to Google Drive, then you can do it. But they will send you a link instead of, yeah. Huh? Okay. So I think this is what we have. Now, we want to come back to the lecture notes now. And I'm not sure whether I should do it now or you want to break for lunch and do it after lunch. This is actually quite a good point to break, because the next part is a bit more mathematical. Okay, the next part I'll be doing is actually this portion. What I want to do is to do the portion on the undrained test. This is the one. Because this part will bring us back to how to describe that particular stress path. You know, the stress path going to the left, you've got a Mohr-Coulomb going straight. A straight stress path is easy to define. A stress path going to the left, you need a curve to define it, right? And the chem clay, actually, you can deduce the curve. You can deduce the curve on chem clay, and you can define it. And chem clay even predict the Skempton pore pressure parameter for you. And there is a very important lesson to be learned. Not because chem clay is good. No. Chem clay always over-predict the Skempton pore pressure parameter. For the original chem clay, all right? Always over-predict. But there is an important lesson. The important lesson is when you see a model with a cap, whether it is a soft soil model or whether it's a chem clay model, the first thing to check it out, how do you check it out? How do you use the A parameter? How do you use the stress path to check it out? It's just, they will all give you a stress path that go that way, but just because the stress path go that way doesn't mean it produced the right excess pore pressure for you. It may still be under-predicting the excess pore pressure. You want to at least know deep in your heart how much it is under-predicting, if it is under-predicting. And can I find the model in such a way that it is at least predicting close to the amount of excess pore pressure? You see, that is all related to the thing about the method A. So that's why that is the part I need to go through with you. And that is the afternoon's job. That is the afternoon's job. Okay, so I will only go through that part. The rest of the thing I will not go through, because I think it's nothing but, there's a lot. In fact, I won't even go through in detail. I will just go through, just because I want to front load a bit of things so that afterwards when we come back, Prof. Junaja has time to bring you through some of the problems. Okay, I think it's important because you need to at least get a heads up on what kind of problems are likely to be coming out, okay, tomorrow, so that you can at least have a mental preparation for tomorrow, okay. You don't want to be completely hit, totally, how should I say, totally cold, you know, then there will be a lot of screaming and shouting, okay. So maybe we just front load this part, just this part alone. I will just quickly run through the mathematics without going into detail. Okay, the question, this part is how do you calculate elastic and plastic volumetric strain? Now, the important thing about the Cham-Clay model is that the elastic and plastic volumetric strain has nothing to do with the U locus. It is all guided by the unloading, reloading line and the normal compression line. So you can just examine the unloading, reloading line if you are interested in just the elastic strain. Okay? So let us think about a simple situation. Imagine you're on the unloading, reloading line or somewhere on the U locus that is, or below the U locus, but a point that is above the unloading, reloading line, okay? A point D moving towards a point A, moving towards a point A. So basically, the mean effective stress is increasing from D to A. So as the mean effective stress increase, how would the specific volume change? And therefore, how does the elastic volumetric strain occurs, or what is the expression for elastic volumetric strain? So basically, very simple. This is the equation of the unloading, reloading line. At point D, we apply to point D, and the specific volume at point D is equals to this constant V kappa minus kappa log of P at D, mean effective stress at point D. All right. Similarly, you apply to point A. This is what happened. You take the difference between the two, VA minus VD is equals to kappa log of PD over PA dash. Agree? This is if you have a finite increase, a finite step from D to A, from D to A. All right. Now, this gives you the change in the specific volume. Now, if you have a very, very small increase, then what you do? You differentiate this equation. You take the differential of this equation. The differential of this equation, okay? You can take dV over dP prime if you like, okay? And then cross multiply across. So dV over dP prime equals to minus kappa over P prime, just differentiating the log. You see the natural log is very easy to deal with because you just differentiate. It's 1 over P prime. And then you divide both sides by V. You divide both sides by V, you get this thing here, dV over V over dP prime equals to minus kappa over P prime V, okay? But you realize that dV over V is actually the elastic volumetric strain increment, d epsilon VE. We have defined that previously. So therefore, this is the elastic volumetric strain increment. This is the epsilon VE, okay? So the epsilon VE over dP dash is equals to minus kappa over P prime V. Take the reciprocal of both the left-hand side and the right-hand side. The reciprocal of the left-hand side comes out as dP prime over the epsilon VE. On the right-hand side is equals to P prime V over kappa. Okay. Now the negative sign goes out. The negative sign goes out because the epsilon VE is equals to minus dV over V. A decrease in specific volume means volumetric compression, which means positive volumetric strain. That's our convention. All right. So basically, that is why the negative sign has basically disappeared. And what you have is dP prime over the epsilon VE is equals to P prime V over kappa. But dP prime over the epsilon VE, this is the rate of change of mean effective stress with respect to volume, elastic volumetric strain, is actually the effective bulk modulus. So the bulk modulus is given by P prime V over kappa. And you realize the bulk modulus of a soil which follows the E log P, not just Cham-Clay, any soil that follows the E log P curve is actually not a constant. It's actually not a constant, because as P prime increases, your kappa your K will increase. As V increases, your K will increase. But it is inversely proportional to kappa. So when you see a soil with a very small value of swelling coefficient or recompression coefficient, that means a high value of bulk modulus. Clear? Okay. So these are some of the key points that you can internalize. So you see, essentially the bulk modulus is roughly inversely proportional to the swelling index. Okay. So this is what it is. And essentially, if you rearrange this, then the elastic volumetric strain increment is just simply equals to kappa dP prime over Vp prime. That's basically what it is. Okay. Kappa is the swelling index. Kappa is this thing. Kappa is this. Okay, essentially kappa is this thing over here, and you can see this is the V log P curve. Okay, but in the standard V log E log P curve, this is actually a common logarithm, base 10. Now we are plotting natural log, so that's why we use the kappa instead of CS or CR. But CS and CR is the swelling index, recompression index. So I would usually call this a recompression index or swelling index as well. Okay, so the kappa is actually a swelling index or recompression index, but on a natural log scale. Is it okay? On a natural log scale. Follow? So basically your bulk modulus is inversely proportional to the swelling index and the recompression index. Fine? If we assume that both the Young's modulus, yes, correct, because the kappa is the bulk modulus is not constant. You remember the Young's modulus and the bulk modulus are related through to the Poisson ratio. If the bulk modulus is changing, increasing, you would also expect the Young's modulus to be increasing. And the same thing with the shear modulus. Okay? Yeah, so if the bulk modulus is increasing and your Poisson ratio is a constant, you expect your Young's modulus to be increasing. If your Young's modulus is increasing and your Poisson ratio is a constant, you also expect your shear modulus to be increasing. Basically, the formula I think is, if I remember correctly, the formula is this: K dash equals to E dash over 3 into 1 minus 2 times nu dash. So if this is a constant and this guy is increasing, this guy's got to be increasing. Okay? So if this guy is increasing, then the G is equals to E dash over 2 into 1 plus nu dash. If nu dash is a constant and E dash is increasing, G must be increasing. Okay? Now, I'm not saying that's realistic. In fact, I think that's unrealistic. That's why the weakness, or people always say, the weakness of chem clay is in the elastic part. Okay? The people who came up with chem clay has never given a lot of thought to the elastic part. And this is something that Andrew Schofield also agreed, that they have not given. Their idea was to match the plastic part first. Okay? And it works for soft clay because you know why? In soft clay, the plastic part usually overpowers the elastic part. The plastic strain is much larger than the elastic strain. So whatever error you incur in the elastic strain is not so important. But if you have stiff soil, you apply chem clay, then you are in trouble. You understand what I mean? So stiff soil, like I said just now, you can apply Mohr-Coulomb with some kind of non-linear, hyperbolic, whatever. You know, that's what. I mean, if you ask Richard Jardine, that's what he told us. Just apply Mohr-Coulomb, I just fit in a non-linear thing. I mean, of course, he's talking about applying it to industry job, maybe consulting job, you know. Okay, but we are here talking about application to practical engineering. Of course, if you want to do something very sophisticated, you may want to do something like the MIT E1, MIT S1 model or whatever it is, which model this kind of recompression, compression, and non-linearity very well, you know. But of course, I think Andrew Whittle's model requires something like 12 parameter or more to get it to work. So, you know, I mean, again, you know, you're back with a problem. You're back up with a problem where you get the 12 parameters. Okay. All right. Any question? Any question? So far, are you all okay with the pace? No? Can you all follow the thing? Okay. Because I'm standing up in front here talking, and I don't know whether I've lost the whole group or whether, but at least you all are asking questions. That's good. You know, back in NUS, though, some of the MSc students, the part-time engineers, they don't ask you and they don't understand the thing. So probably back deep in the mind, they're asking, what the hell is going on? You know, and it comes out in the exam. What the hell? 20 marks. You know. So okay. So far, yeah. On the wet side of critical, yes.
When unloading it is coming like,
Yes, it's straight, because it's elastic.
so if I am relaxing the axial strain, the pore pressure will be remaining.
The pore pressure will not remain the same. Actually, the pore pressure will not remain because your total stress path is decreasing. Afterwards, I will talk to you about that. Because there are two components of pore pressure. One component arises from the change in the total stress, mean total stress. The other component arises from the shear. So basically, when you unload, you are reducing your mean total stress. So your pore pressure will show up as a slight drop as well. It will show up as a drop. But you can only do it when, after lunch, we look at the total stress path, we look at the effective stress path, and you see there are actually two components of pore pressure. Okay? Okay? Anyone else? No? Okay? Yeah. Decreasing. Yeah. Contracting, yeah. Softening. Yeah. Not exactly the same. Okay, my understanding of sensitive soil, to be honest, I have not worked on sensitive soil, but I worked on cement treated soil quite a lot. Okay, in fact, just now the work I showed the paper was on cement treated soil. We observe a lot of softening, and that softening comes about not because of volumetric dilation, but because you just break the bond. So it's different. That's why you cannot use chem clay to describe that class of soil. Cemented soil or naturally cemented soil is not readily described by something like chem clay. In fact, I am not even sure if there are any model in any of the commercial program. I don't think soft soil model describes it, because destructuration is still an ongoing science. It's still an ongoing science. We call it destructuration, which is loss of structure of the soil. The microstructure of the soil is being destroyed. That is still an ongoing science. And my sense is chem clay cannot do it. Modified chem clay cannot do it. Okay, Mohr-Coulomb of course cannot do it. Hardening soil cannot do it. Hardening soil can only do something relating to the unloading, reloading, knot, that kind of thing, for hardening. Soft soil model cannot do it. Okay, I don't even think Abacus has any soil model that can do it. Okay, I mean, if you want, you got to look at the paper we wrote, just published this year, which is on the bounding surface on cohesive chem clay. Cohesive chem clay. We actually have a chem clay that has a cohesion, built-in a cohesion, and that cohesion actually starts at a high value and it drops to 0 to simulate the loss of structure. Now that can do something like that. So you need something like that, but at the moment there's none of this model in the standard program. So we actually coded in our own model into GeoFEA, using a user-defined model interface. Okay? Is that okay? Yeah. Unfortunately, this doesn't exist right now. Okay? Any other question? Okay. So I think the lunch is the usual place. I think up the rooftop, right? Okay. Thanks very much for your attention.